Most of these older data access technologies suffered from either or both of two basic flaws. The first is that they were really too close to the metal of the underlying data stores, most often relational databases, which requires writing application code that was radically different from business logic and user interface code. This was particularly true as object orientation became the standard programming methodology. Relational databases are decidedly non-object-like, and often applications would have SQL statements hard-coded and embedded within them. So you're doing this context switch constantly between Visual Basic or C# or whatever your programming language is, and Transact SQL, and the two languages are completely different. And then the other basic problem is that they use generic data objects that were ideally suited to contain and work with two-dimensional data, the classic rows and column structure of a record set, but were often extremely difficult to incorporate logic and behaviors that useful business objects really should have. For example, an ADO.NET dataset object is a great, albeit pretty heavyweight, data container that can keep track of changes to data and manage persistence back to the data store. But you can't easily incorporate business logic in a dataset or turn it into a custom object with properties and behaviors useful to the application. You could encapsulate it and do various things like that, but it was really kind of it's just a kludgy workaround to get the generic data object to work. And as a result of these two basic flaws, developers have historically spent a significant part of their work writing custom data access code for each new application, overcoming the generic nature of those data access objects, and often wrapping them with custom objects that more closely model real-world objects. A large part of the problem with the older data access technologies is that they did nothing to overcome the mismatch between relational database code and object behaviors in a true object-oriented application. SQL in a relational database is set-based and procedural, while objects have properties and behaviors and raise and respond to events. This means that your data access code not only had to manage the flow of data between the application and the data store, it also had to bridge the fundamental difference between native database code and application code, as well as the data structures. And this was never a simple task, and developers had to write custom code to bridge the difference for each and every application, which is a huge time sink. ADO.NET Entity Framework is Microsoft's technology to bridge that database application gap. Entity Framework is an object relational mapper, or an ORM, which manages the interface between the application code and a data store. Using various models, it generates the code to create true business objects that integrate nicely into an object-oriented application while managing the flow of data to and from the data store. Entity Framework provides a variety of tools to build a robust object-oriented data layer, including Visual Studio Designers, an API to give you programmatic access to a rich object model, and various runtime services. And best of all, it has matured into really a useful dynamic data access technology. So that's what this course is about. But first, I'm going to continue on and talk a little bit more about this disconnect between data access technology and relational databases. I do want to mention one thing about terminology. In this course, I'm often going to use the terms data store and database to refer to the same thing. And that's the location where application data is stored persistently. So you save data between application invocations. The difference between these two terms is pretty subtle. A data store, as really I'm using it here in this context, is a generic term for data stored in almost any kind of form, including XML files, text files, an object database, relational database, and, perish forbid, Office documents like Excel spreadsheets. A database, on the other hand, usually means a relational database. Since you'll probably most often use Entity Framework with a relational database, although you can use it with other data stores if you have the provider that understands the data store as well as Entity Framework, then the two terms are essentially synonymous. Now, once I move beyond the basics of object relational mapping in the Entity Framework, then I'm pretty much almost exclusively going to be using the term database. But don't let the two terms, my use of the two terms, confuse you in any way. They're essentially the same thing as I'm using them here. All right, so let's talk more about these object relational differences. As I mentioned, one of the primary problems that any data application has to overcome when it uses a back-end data store to persist its data is the inherent differences between the use of strongly typed objects in an object-oriented application and the data structures and both set-based and procedural nature of a data store and its code. The problem is ultimately that somewhere in the application, or sometimes in the data store if it's programmable, there has to be a lot of code to handle the differences that arise from these two very mismatched systems. How you choose to handle these differences is going to have a big impact on your application's design, the development effort that it takes to implement the application, as well as performance. All right, so the first big difference I want to talk about is data type differences. The number of possible data types in a data store is limited only by the creativity of the system's developers to respond to the needs of data stored there. They range from simple things in an XML file to the rich data types available in SQL Server. And here I have a table that lists most of the data types in SQL Server. But it's important to understand that each new version of SQL Server seems to expand on this list, or at least make subtle changes to the types that are available. Now, most of the data types listed in this table have fairly direct equivalents in .NET. All of the string types, char, varchar, and text, for example, and their Unicode versions, map nicely to a .NET string, although there needs to be metadata available so that the length and other constraints are met when storing strings. In other words, if I create a string in a .NET application, I can store essentially 2 gigabytes of data within it. But it's highly unlikely that, well, it may not be highly unlikely, but most text fields in a SQL Server table are not going to allow unlimited amounts of text unless they're defined as varchar max. Now, the integer types map reasonably well, but a tiny int maps best to a .NET byte. So that's a little bit of a disconnect between the different types of data. The date and time types map reasonably well to the .NET datetime and time span types, although there are data range differences that you have to be careful with. Another example is that the only option for a SQL variant is system.object, unless you know the underlying type and can make a better .NET data type selection. So as you examine the potential mappings more closely, it really very quickly becomes apparent that there are many potential issues in mapping the data, and precious few data types have exact equivalents on both sides, in a relational database and in your .NET application. As a result, you have to be very careful when moving data between a database and a .NET application. Now, another issue that I kind of alluded to earlier is that types in the database have various constraints. Often, they're related to the storage requirements for the data. So, for example, char and varchar and their Unicode equivalents have a maximum length when you use the types to define the type of column in a table. And this limits the space available for the type storage. It's a big factor of making data storage more efficient within, say, SQL Server. But a .NET string has no such limits, other than, as I mentioned, its 2 gigabyte maximum length. And there's no way to declaratively limit the size of string data stored in the .NET string type. So you have to perform those kinds of checks programmatically if you really need to limit the length of the text to, say, 30 bytes or whatever. And then yet another issue with these data type differences involves binary data. SQL Server has a single generic binary data type that lets you store images, Word documents, video files, and many other kinds of data. In .NET, you could use a byte array for that kind of data, or you can use a more appropriate type, such as an image for image data. And then the SQL date and time types present another set of issues, because you have only the date-time type in .NET to store that data. When you move date and time data back and forth between the database and .NET, you have to be careful not to inadvertently modify the data to add values where none exist, such as by setting the time to midnight when you really don't have time information, because midnight is usually the default time when you create a date-time type. All right, so that's one kind of differences that an application has to deal with when working with a data store. Another type of difference is relationship differences. So much like romantic relationships that you might have, relational databases and objects in .NET have fundamentally different ways of maintaining the relationships between related data. It does kind of sound like Venus and Mars. Relational databases use foreign key constraints to indicate that the data in one table is related to another table in a specific way. And it does this by storing a piece of data in a related table that uniquely identifies a row in the master table or the parent table that defines the relationship. So for example, in this image, the sales order header table in the sample AdventureWorks LT database has a primary key sales order ID. And I have a red arrow pointing to that in the left table. And then each sales order has one or more order details stored in a related sales order detail table, which is on the right, which includes that sales order ID as a foreign key into the sales order header table. All right, and so the image there shows how this looks within a database diagram. Now, in contrast, .NET maintains relationships between objects using object references. There are a variety of ways to implement this in a class, but one way is to have what are sometimes called navigation properties, which is actually the entity framework term for it. And you have these navigation properties in each object that are related to other objects. For a one-to-many relationship, for example, the master object would have a collection property with references to multiple child objects, each of which has a property referencing that same master object. Okay, and so the image shows how you could implement this for the sales order header and order details table, again within the AdventureWorks LT database. The sales order details collection property in the sales order header entity, down at the bottom of the left part of the figure, contains the details of the order. And then the sales order header property in the sales order detail entity contains a reference to that master order header. Okay, so it's just a fundamentally different kind of relationship between the objects in .NET and the tables within a relational database. Now, the cardinality of the relationship that I show here in the figure as the 1 on the left side that I have circled and the asterisk at the other side. So that's the cardinality at each end of the relationship, and it links the two entities together. The 1 means that there is one order header for each order detail. And the asterisk means that there are an unlimited number of order details for each order. And that's implemented as a collection property within these .NET objects. What that means in effect is that you can have a sales order header that has 0, 1, or more order details. Okay, then another option is many-to-many relationships. The AdventureWorks LT database implements that kind of relationship to store customer addresses. A customer might have many addresses, street, mailing, billing, etc. And those addresses could be shared, such as shared billing address for company branches or the same home address for a husband and wife. Well, one hopes, I guess. So this image shows how the AdventureWorks LT database stores that data, using a customer address table to store the related data. Notice that the table also stores additional information about the relationship, the address type, a row GUID, and the relationship's last modification date. And then this image shows one way, not the only way, but one way to model the relationship between customers and addresses within the database. In this case, each object has a collection navigation property that provides a reference of all addresses for a customer and all customers for an address. The cardinality of the relationship is also changed because it shows an asterisk at each end of the relationship, which means many customers can be associated with any address, and many addresses can be associated with any customer. As a result, the navigation properties are implemented as collections, and the property names are pluralized by default within Entity Framework. Now, I do want to point out that the entity objects that I show here in the figure in this particular example are not the default objects that Entity Framework creates for these tables. The reason is that the many-to-many table in the database, customer address, has columns in addition to the 2 foreign keys that are needed to link the customer and address tables. As a result, Entity Framework creates a third linking entity object, again by default. And you'll see how this works in other parts of the course. But you can easily change the Entity Framework model to create the objects that I show here. But it's important to understand you'd only want to do that if the application doesn't need to work with the extra fields within the many-to-many table. Okay, so just file that away for later as you're becoming more familiar with Entity Framework and working with different kinds of relationships between tables. Okay, so bottom line of all this is that there's quite a difference between how a database stores data and how an application represents the data as entity objects in memory and relates the data. Big differences. Next difference I want to talk about is inheritance differences. As a true object-oriented language, C# and .NET has strong support for object inheritance, as does Visual Basic and most other .NET languages. Inheritance is a means to compartmentalize and reuse object properties and behaviors. You can accomplish this by defining an object with all shared features, and then derive other objects that inherit those base features and then extend them. This is a great way to create a group of closely related objects that have similar characteristics without duplicating code. Now, the single major inheritance feature that C# doesn't support is multiple inheritance, which is the ability to inherit directly from 2 or more objects. But this really isn't much of a shortcoming, because multiple inheritance is a major cause and source of bugs in languages that do support it, for example, C++. Inheritance is a great feature in the many programming languages that support it because it makes code simpler, more maintainable, and easier to debug. Largely because it lets you more accurately model real-world things and reuse code instead of copying it over and over again in different objects. It lets you model hierarchies of objects, such as the product and parts assemblies that go into building any complicated machine, such as an automobile or an even larger scale, a modern jet. The problem here is that relational databases don't natively support inheritance, or at least most don't. You can create tables related by foreign keys, but there's no concept of layering of tables so that one table contains the data for the base properties and others contain only the additional properties needed for derived objects. As a result, it can take some work to create a database schema that supports object hierarchies through inheritance in the application. Now, that doesn't mean that there isn't support in a relational database engine like SQL Server for building these kinds of objects. It's just that it doesn't do it automatically. You have to do a fair amount of work in order to put all the pieces in place. And there's various ways to do it. One is to create a base table with the core data for the base object. And then you create additional tables for each inherited object's data. And this is referred to as a table per type approach. All of the related tables would have a one-to-one relationship with the base table. Now, as you can probably imagine, this kind of scheme can quickly grow to be very complex, particularly if you have multiple levels of inheritance, where an object inherits from one object, which inherits from another object, which inherits from another object. It's single inheritance up the line, but it's multiple levels of inheritance. Another way to do it is to create a separate table for each type in the object hierarchy, and you duplicate the base fields. And this is referred to as the table per concrete type approach. This is not directly supported by the Entity Data Model Designer and causes complications for the mappings between the conceptual and storage models, but you can do it within an Entity Framework. And then the third major way of doing it is by creating a single ginormous table that contains all of the base data as well as fields for every additional property of every derived object. and this is referred to as the table per hierarchy approach. This has the benefit of not littering a database with many tables, but the single table can grow to contain an enormous number of fields, possibly reaching the database's field limit, which is 1024 for non-sparse tables within SQL Server. Now, besides the complexity of the table schema, in order to support different kinds of inheritance, you have to manually manage special constraints. For example, because .NET languages support only single inheritance, you need some way to make sure that the data for a single object is stored in at most two tables, the base table and no more than one of the tables for derived objects for the base table option. If you're using the single table option, then you have to make sure that only the fields of the table for the base object and a single set of fields for a derived object are stored. All other fields for other objects have to remain null because they're not used by that derived object. This requirement isn't something you can implement using regular database constraints. Instead, you'll have to either implement a series of complicated triggers to control the data, or be disciplined enough to do it entirely and correctly in every application that uses that object hierarchy. So no matter what you do, implementing inheritance in the database is going to add some serious complexity to both the database and the application. The last big difference I want to talk about between the use of objects in an object-oriented application and the data structures of a data store is how you tell that two objects are equal, that they have the same or a different identity. And those are actually two different related concepts, equality and identity. Enforcement of a unique primary key, which is called a primary key constraint, is a feature of every modern database system, most certainly including SQL Server. This makes the selection of a table's primary key an important decision, including whether you select a natural key, which is one or more fields that contain actual data about the object, or a surrogate key that doesn't use values of any inherent value to the object, such as an identity value that by default starts at 1 and increments by 1 for every new row that you insert into the table. This is quite different from the concepts of equality and identity of objects in an object-oriented application. If you have two objects in memory that contain the same data, the application may even have loaded the data from the same row within a database. They are not equal and therefore don't have the same identity as far as the application is concerned. If you have two variables, each of which holds a reference to one of the objects, then those variables are not equal. Only if both of the variables hold a reference to the same single object in memory does the application considers them to be equal. And this is called equality by reference. You could, however, define what equality and identity mean for custom objects in your application. For example, you could define a method that compares the values of each of the properties of two objects and declare them equal if all of the properties are equal. But this isn't as easy as it sounds, because object property types can themselves be objects. In that case, you'd have to decide whether you need to recurse into those object properties or fall back on the default concept of equality where multiple properties have to hold a reference to the same object in memory. And often, it's a different decision, different way that you handle that for different properties within the same object. So it gets really complicated really fast. So what all this means is that even something as fundamental as equality and identity is handled quite differently in a relational database and object-oriented programming, which means that you have to have code in your application that overcomes these differences. So, as you can imagine, it can be an enormous amount of work to write code in an application to handle all these fundamental differences between relational databases and an object-oriented application. The good news is that these differences are nothing new. Developers have been grappling with them for many years and have come up with various patterns and strategies for handling them. But just because a problem is well understood doesn't mean that it's easy to implement. Handling the differences as flexibly as possible to handle every situation can take a lot of work and result in some very complex code. But even if you develop a custom solution for the issues faced by a single application, it can be a lot of work to implement.